Reversible reactions reach an equilibrium when the rate of the forward reaction equals that of the reverse one. Doesn't mean that the reactions stop, but it does mean that the concentrations of the reactants and products are constant unless the conditions are changed. So let's say we have a gas reaction that we'll write in terms of our coefficients as well as our products and reactants. If we want for a gas reaction to write the equilibrium constant, we write it in terms of the partial pressure. So this would be the partial pressure of C, big C, raised to the little c, the same with D. And notice it's products over reactants. So one of the things that we have to be careful of are those coefficients that our partial pressures are raised to. So we're going to look at an example of a gas reaction, and this is the formation of ammonia. We would normally write this, the partial pressure of ammonia squared, because there are two of them, divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. In material and energy balances, however, we often write the K in terms of mole fractions. But you have to be really careful in using mole fractions because you need to remember that this is really a partial pressure. You might try and write it like this, just using the mole fractions. However, this is incorrect. So let's write out our partial pressures in terms of our y's. And I'm just going to use y sub I for each one of these mole fractions. So this is squared. This is not squared because it's just N2. And this one is cubed. Therefore, if we want to write it only in terms of mole fractions, we have to make sure that those extra pressure terms stay in there. So instead, we're going to write it like this. And when we cancel out the pressures, we find that this has to be multiplied by 1 over p squared. Let's take a look at an example. In this problem, we're going to use the extent of reaction to find the number of moles at equilibrium. So the number of moles of nitrogen is going to equal the 4 that came in minus the extent of reaction. The number of moles of H2 at equilibrium is going to equal 8 minus 3 times the extent of reaction. And the reason we use that 3, again, if we go up and look at the reaction, the stoichiometric coefficient is 3. The number of moles at equilibrium of ammonia, and that, because there's nothing that comes in, is just 2 times the extent of reaction. And we're going to put an E by each one of these since we are in equilibrium. Now let's set up the expression. Since we need the mole fractions, we're going to need the total moles. So if we add these up, we're going to end up with 12 minus 2 times the extent of reaction. Let's write all of the mole fractions in terms of the extent of reaction. So here are our mole fractions at equilibrium. We can put it into our equilibrium expression. This is what it looks like. However, you have to be careful because remember we have that pressure term. So this whole thing has to be multiplied by 1 over p squared. My suggestion is that at this point you put it in some kind of computer program to solve for this extent of reaction. You might suspect that there's more than one possible answer, but if you look at your possibilities, what you'll find is that the extent of reaction at equilibrium is 2.07. In order to find our compositions, which is what we were looking for, we go back to how we described our mole fractions, and we put in the extent of reaction that we calculated. And one way to check that you have used the right extent of reaction is that, as happens here, the sum of your mole fractions equals 1.